So today we are going to look at the proof of this, proof of statement and proof of the D'Alembert's ratio test. As we know, we are in the series of videos on infinite series, mostly of positive reals. So let me start with the statement. So we state D'Alembert's ratio test as follows. It can be stated as a theorem. So let summation un be, as usual, a series of positive terms, and this ratio, limit of un plus 1 by un as n tends to infinity, be expressed as L. Okay. Now the what we infer is from this L. Then if L is less than 1, we conclude the series is convergent. If L is greater than 1, we conclude the given series is divergent. So let's work on this proof. So again, you remember we did something called as Cauchy's and Throat test. So similarly here also, we are going to first go by definition of what this L is all about. L is the limit of this ratio, right? That's exactly what I wrote here. It's un plus 1 by un, that ratio. That is your L. So this implies that by definition, for all epsilon greater than 0, there exists m belongs to the natural numbers such that after this point, this ratio un plus 1 by un getting close enough to L and is bounded by epsilon. This whenever n is greater than m. This is true whenever n is greater than m. Right? So we can do this simple mechanics that by opening the modulus sign, we get minus epsilon less than un plus 1 by un less than epsilon, which implies L minus epsilon is less than un plus 1 by un. I think I should have written minus L here. Yeah. So this term is bounded between minus epsilon plus epsilon, and now I add L in each term and I get less than L plus epsilon, right? So now we reject or ignore the first step, the first m terms, so that we are in the case that my n is greater than m. Ignore the first m terms, and then we can say that for all n, this holds. What is that? L minus epsilon is less than un plus 1 by un less than L plus epsilon. Now let me concentrate on this number L plus epsilon. Let epsilon be chosen such a way that we know that yeah, I think let me start afresh. Let L be less than 1. That's what I wanted to say here. We know that L is less than 1. So choose epsilon such that L plus epsilon is still less than 1. Then we can give a new name to this. Let's call L plus epsilon equal to R. So L plus epsilon equal to R is less than 1. Now with this setup, the fact that this ratio un plus 1 by un is less than R for all n, because I've rejected the first m term, so for all n, without loss of generality, we can say for all n this is true. And this implies that you can write un. Okay, now I'll rather consider un as un by un minus 1 into un minus 1 by un minus 2 into un minus 2 by un minus 3. I can go on till, see, we are decreasing, so eventually you'll go to this, eventually you'll go to this. So we have it as un only because we cancel all these terms. So I've just multiplied and divided by un minus 1, multiplied and divided by un minus 2, and so on. So it's the same thing as un. And now this right hand side is same as, because every no, we should not say equal to, we should say less than r, because this term is r, less than r, this term is again less than r, this term is again less than r, and so it is less than so many times r times un. So therefore what we get is un, which is equal to this expression, is less than r power how many terms? You have n minus 1 terms times un for all n. Now you know that u1 is a positive term. So what we get here is a, so every term in my summation un is less than a constant times, what is that constant? That constant is I think I'm writing in the wrong slide, so let's repeat this. Yeah, here I'm here. So every term in summation un is less than some constant times r power n minus 1. This is a geometric series. This constant is u1. So what we infer from this is that it behaves like the geometric series. Therefore, summation un behaves like the geometric series. R n minus 1, and we know that this R is less than 1 because R is nothing but L plus epsilon. We've chosen epsilon such that L plus epsilon is less than 1, so R is less than 1. Therefore, this, since the geometric series on the right converges, so our given our given series also converges. That's the argument for the case 1. Let's look at the argument for case 2. Case 2, let L be greater than 1. Now you see, just like in the Cauchy test also, we will look at the other side inequality. We know that L minus epsilon is less than un plus 1 by un, implies un plus 1 by un is greater than L minus epsilon. So now choose. So now we know that L is greater than 1. Choose epsilon such that L minus epsilon is still greater than 1. Okay. So now what we get is a situation like this. You can write now, you can write un just like the previous one, un by un minus 1, un minus 1, un minus 2, un minus 2, un minus 3, so on up to u2 by u1 times u1. Now again, this I can state, I can quickly state here that this is greater than, if I write this, replace this by, let's say, R, let's call it as R. So my un is greater than R times so on up to R times u1. Therefore, un is greater than R power n minus 1. These are n minus 1 terms times u1. Therefore, every term in summation un is greater than corresponding term in the RHS. And what is that? Which is nothing but a constant times a geometric series term. And since the geometric series has R greater than 1, the geometric series diverges. So the left hand side also behaves the way the RHS behaves. Therefore, our series summation un diverges because every term is greater than a divergent component of the divergent series. So eventually the sum is going to go to infinity. That's what we claim. So hence case 2, that is if L greater than 1, summation un diverges. That ends the proof. Thank you.